This is problem 3 on practice exam 2 of module 8 in the book Problem Solving Guide for Mechanics and Thermodynamics. There's an experiment to study the dynamics of a collision between a bat and baseball. So the bat's horizontal, hinged here, center of mass is 20 inches from the thin end. It's released from rest here, swings down, hits the ball. Bunch of parameters here. We can get to those when we need them. When the bat is released from the horizontal position and allowed to swing down, what is the speed of the end of the bat when the bat's vertical? Just before it hits the ball. That's part A. Part B is I put a baseball here, which has a mass of 145 grams. The bat hits it. The ball takes off with a speed of 4 meters per second. What happens to the bat after the collision? What's the angular speed of the bat after the collision? Okay. There's a diagram there. Part A is clearly a conservation of energy problem. One mass is involved, it's falling. The torque on the bat from gravity is decreasing as the bat rotates. Gravity is always down. The perpendicular component is high here, it's the whole 20 inches. But as soon as the bat starts to fall, the perpendicular component gets smaller. So the torque changes. If the torque changes, the angular acceleration changes. So all of those equations of kinematics are out the window because the angular acceleration is not constant. We have to use energy. So we're going to define gravitational potential energy level equals 0 at the ball, right here. And now the bat is 20 inches above that level. We got inches. Let's get meters from that. 39.37 inches in 1 meter. You didn't know that? Good for you. It's on the test. Or you raise your hand and ask me. You have to memorize any unit conversions like that. So we get about half a meter, a little bit more than half a meter. Now we can get the initial energy in joules. It's all the gravitational potential energy of the bat. There's the mass, it's given, 1.22 kilograms. There's the gravitational field strength, and there's the height, 6.2 joules. That's the initial energy in the system. The final kinetic energy before it hits the ball, we're going to get thermal energy generated. We don't want to hit the ball. We're just going to go the bat swing. That's all. Pure rotational of the bat. That's E final. The moment of inertia is given. We have the initial energy, 6.2 joules. We can set the initial energy equal to the final energy. We can calculate omega, and we get 4.98 radians per second. Before the bat hits the ball. Just before the bat hits the ball, the bat's rotating at about 5 radians each second. Question asks for the speed of the bat. We can get this with V is omega r. And the end of the bat's 30 inches away. So we can calculate the speed is 149 inches per second. We can convert that to meters per second if you want. 3.79 meters per second. All right, now part B. Ball hits the bat. The ball rebounds 4 meters per second from the collision. We have to figure out what the bat's doing. The hinge is going to exert a force on the bat, so linear momentum is out. If we conserve angular momentum about the hinge doesn't exert a torque about this point, so we're going to be okay. So we know the angular speed of the bat, and we know its moment of inertia, so we know the initial angular momentum in the system just before the collision. It's I omega, and we calculated omega was 4.98 radians per second. I is given, and we get the initial angular momentum, 2.49 kilogram meters squared per second. The angular momentum after the collision is that of the ball and the bat. We know what the ball's doing. We have to calculate what the bat's doing. So I omega is of the bat, MVR is of the ball. We're going to treat the ball like a point mass. Substituting in the knowns, we got the moment of inertia of the bat, angular speed of the bat after the collision, and mv of the ball after the collision times the perpendicular distance of 20 inches, which is 0.508 meters. It looks like we can set these equal and solve for omega final. So that's L final with all the numbers in it. setting the initial and final equal. We only have one unknown, the angular speed of the bat. And we get 0.44 radians per second. It should not be too surprising that the bat doesn't bounce off the ball, right? This bat's coming down here. When bats hit balls, the bat keeps going. So the bat started out at 4.98 radians per second, hit the ball, and continues forward, rotating with 4.4 radians per second. That's problem 3.